Have you ever wondered what it would be like to create an AI that can play classic video games? In this video, we're going to explore just that by creating an AI to solve a classic Mario Brothers screen. Machine learning has revolutionized the field of artificial intelligence and has seen tremendous advancements in recent years, especially in the realm of gaming. For example, Google's AlphaGo used machine learning to defeat the world champion in the game of Go, and OpenAI's Dota 2 AI learned to play the game at a professional level. Video games have become a popular domain for researchers to test and refine their algorithms, and machine learning has enabled us to create AI agents that can learn from their environment and become better at the game over time. With games like Super Mario Bros., we can create AI agents that learn to navigate the game's environment, avoid obstacles, and defeat enemies. It may seem simple, but the game is quite challenging, even for humans. With so many obstacles and enemies to overcome, it's the perfect game to test the abilities of an AI. In this video, we'll be using a machine learning technique called reinforcement learning to teach an AI to play Super Mario Bros. We'll start by setting up the environment and then move on to training and fine-tuning the AI until it can flawlessly navigate the first level of the game. So, let's dive in and see what we can create. Welcome back. Now that we have set the stage, it's time to embark on our journey to create an AI that can conquer the iconic Super Mario Bros. Screen. In this video, we're going to be focused on building a full-blown reinforcement learning model or AI model for Mario. And to achieve that, we'll be going through 4 key steps. So, first up, we're going to set up Mario. Then, we'll take a deep dive into how we pre-process the environment. After that, we'll move on to training our reinforcement learning algorithm. And finally, we'll put our AI to the test. First things first, let's see if we can play Mario using Python, considering the fact that we'll be using Python throughout this tutorial. Feel free to use your preferred Python editor. Before we proceed, let me provide you with the Python version, just in case you encounter any issues. Now, let's move on to setting up Mario. We'll be using OpenAI Gym, a powerful toolkit for developing and comparing reinforcement learning algorithms. To install OpenAI Gym, simply execute these 2 commands. Don't worry, in the following section, I'll explain what Gym Super Mario all is about. The algorithm we'll be using for our model is the proximal policy optimization with the stable baseline 3 implementation. We'll need to install this algorithm as well. Before we dive into the exciting world of pre-processing and AI, let's get our environment up and running. As mentioned earlier, we'll be using the Mario AI tool. With this tool, you can create different environments based on your preferences. We have the standard version, one with pixels, and one with rectangles. You can choose whichever environment you prefer, as the pre-processing and training will work in the same way. However, if you choose an environment with fewer pixels, like the rectangles, the training process will be faster. Here, the tool also explains that we can load different levels, but for this video, we'll be focusing on the first level. If you'd like to learn more about the tool, feel free to explore the additional information provided. Additionally, there's a reward function available, although we'll create our own reward function in the next step. It's still interesting to take a look at it. And finally, we have a dictionary with all the elements that we can interact with. For this video, we'll use the standard version of the tool. To create the game environment, use the version with v0 at the end, and with the following command, you can initialize the environment. If you wish to use another version, consult the wiki for instructions on how to initialize it. Next, we need to decide how many inputs and outputs our environment will have. The library comes with a few options by default, such as simple movement, complex movement, and write only. The more possible movements, the more complex it will be for our AI to achieve its goal. Before starting this video, I compared the options and decided to use simple movement, as the complex movements were too numerous and the write-only option had similar results. With these decisions made, it's time to start the game. If you execute the commands below, it will run the game. However, please note that if you're using Google Colab, you won't be able to render the game since rendering isn't supported in Colab. There are alternative methods, like creating a recording, but for simplicity, I recommend using Visual Studio Code. To do this, you'll need a GCC compiler on your computer. Personally, I found it easiest to download Visual Studio and install the compiler. But at this point, rendering isn't necessary. If you want to verify that everything is running smoothly, you can add a print statement to display the variables, confirming that the game is running. Don't worry, at the end of the video, once our model is trained, we'll switch to Visual Studio Code and witness our AI in action. Well, if everything is working, our game should be up and running. It's time to move on to pre-processing. The first tool we'll need for pre-processing is already imported. By activating this block, we'll have all the necessary tools at our disposal. Now, let's begin with the pre-processing steps. First and foremost, we'll tackle the skip frame function. By default, the game performs a movement and returns the reward for that action in each frame. However, training our AI doesn't require an action in every single frame. With the skip frame function, the environment skips unnecessary frames and executes actions every X frames, in this case, every 4 frames. The function sums up the rewards obtained in those 4 frames and returns the total. The next step is rescaling the environment. By default, the environment has a size of 240 by 256 pixels. However, all these pixels serve as input for our neural network, which can be excessive and unnecessary for training our model. To optimize the model's performance, we'll rescale the environment to a smaller size, such as 80 pixels, reducing the number of inputs and improving efficiency. Although the tool itself has a predefined reward, we'll be creating our own reward function. The function calculates the reward based on the game progress. Moving further to the right will yield higher rewards, while dying will result in significant penalties. You can choose to use the provided reward function or create your own, exploring different gameplay modalities such as rewarding points for defeating enemies or collecting coins. Next, we'll address the color scale of the environment. The original environment consists of pixels in a 240 by 256 by 3 format, where the 3 represents the color channels. However, our AI doesn't require color information and doesn't benefit from the additional complexity it introduces. By converting the environment to grayscale, we reduce the color channels from 3 to 1, effectively simplifying the input data. Finally, stacking frames is a crucial step. With only a single image, our AI would struggle to interpret the movement and velocity of Mario and enemies. To overcome this, we pass 4 consecutive frames to our AI, allowing it to better understand the dynamics of the game. This can be achieved using the following 2 lines of code. To summarize, we have applied all the pre-processing techniques discussed. You can execute the provided block to perform all the pre-processing steps. Now, if we reset our environment, we can observe that the resulting shape is 1 representing the color layer by 84 by 84 by 4 representing the stack frames. We have also created a function to visualize these frames. By executing the function, we can observe the stack frames. Please note that the displayed colors may not appear as grayscale due to the library used for visualization. With this step completed, we have accomplished the most challenging part of the training process and are ready to train our model. First, we need to import all the necessary tools for training the model. Take a look at the code snippet below, where we define parameters such as the learning rate and number of steps. These are more advanced concepts that we'll leave as they are for this tutorial. If you're curious, feel free to experiment and share your experiences in the comments. As mentioned in the video, we'll be using the PPO algorithm for training our AI model. However, you can also try different algorithms like DQN or DDQN. If you decide to explore those alternatives, please share your results and feedback in the comments. It would be great to know your experience. Before we begin training, a convolutional neural network has been created. However, understanding the intricacies of neural networks and algorithms is beyond the scope of this tutorial. If you're interested in a more in-depth tutorial on these topics, please let us know in the comments. Moving on, let's create a file to store the records of each training step. This will allow us to analyze and compare solutions later on. In this case, we'll create a folder called model and save a CSV file named reward log. The CSV file consists of 3 columns: the timestamp, average reward, and best reward achieved. Although not shown in this video, I highly recommend saving this reward log in your Google Drive along with the trained models. This ensures that if the execution stops at any point, you won't lose any progress or trained models. Next, we define the callback function for training. This function handles what happens during the training process. As you can see, the rewards are saved, and the best and average rewards are printed. You can also add additional columns to track the win rate, coins earned, or monsters killed. However, for simplicity, the provided data is sufficient. These data will be saved in the CSV file we created earlier. Finally, we need to specify the folder where we want the data to be saved. In our case, we've chosen the models folder. Then, we can start training our model. As you can see, our model will have all the parameters and data we defined at the beginning of this section. Please note that the training process may vary in duration depending on your computer's power, the chosen Mario environment, and the defined parameters. In my case, I trained the model for several hours, stopping at 105 steps. If you're interested, you can explore the generated CSV file to analyze the training progress. By following these steps, you'll have multiple models to test your AI with. Depending on the rewards obtained, each model will have varying capabilities in completing the level. We've reached the conclusion of our AI training journey, and it's time to witness the remarkable results achieved by our trained models. As mentioned earlier, besides the model explained in this video, we also trained another model using the rectangular version of the environment. By analyzing the training graph, you'll notice that the model with the rectangular version required significantly fewer steps to achieve the same score as the standard version. This highlights the advantage of choosing the appropriate environment for AI training. With the training data compiled in the CSV, we can quickly determine the model with the highest average score using a function. For the standard version, the best model was identified at a specific epoch. Let's put our best AI model to the test. With a couple of lines of code, we can load our most successful model and evaluate its win rate. In my case, the model achieved an impressive 20% win rate. Comparing this result with similar studies, it's evident that our model performed exceptionally well, thanks to the PPO algorithm used for training. Now, the moment we've all been waiting for, watching our model in action. Below, you'll find the code block to see our AI play Super Mario Bros. I used Visual Studio Code for this step, loading the model and executing the block with the render function uncommented. So let's see the result video. I hope you've enjoyed this video. You'll find all the code used in the description below. As this is my first video, I eagerly await your feedback in the comments. Please let me know what you thought of it and how I can improve future videos. If you'd like to see more content, such as videos on other algorithms or explanatory guides on neural networks and the PPO algorithm's inner workings, do let me know in the comments. Before we part ways, I'd appreciate a thumbs up and your subscription to stay informed about upcoming videos. Thank you for joining me on this thrilling AI adventure. Until next time, happy gaming and coding!